So this is number 10 of Calculus Math 60 Practice Exam Chapter 4. Here is a function, and notice it's a rational with trig functions in it, which makes it a little bit more challenging. The domain is when the denominator cannot equal to 0. So when you set this aside, when is cosine of x equal to -1? This happens when you have n pi, where n is odd, right? So if you have pi, 3 pi, 5 pi, etc., that's where it'll equal to 0 in the denominator. So domain is all real numbers such except when x is equal to n pi, where n is odd, an odd integer. And you'll get asymptotes at that point. Okay, the x-intercept is when y is equal to 0. So when you set y equal to 0, you set the numerator equal to 0, and that happens when x is equal to m pi. In other words, when m is even. So for example, when x is 0, when x is 2 pi, or when x is at 2 pi, 4 pi, etc. So sine x is equal to 0 at that point. The y-intercept is here when x is equal to 0. So when you plug that in, you end up just getting the origin 0, 0. Symmetry is it even or odd? Well, when you plug it into these two definitions of even and odd, you find out that it is odd. The reason why it's odd is negative sine x is equal to sine negative x, because sine is an odd function. And 1 plus cosine is equal to 1 plus cosine negative x, because cosine is an even function, so that's why these two are the same. So therefore f is an odd symmetry, which means that it's symmetric about the origin and has a period of 2 pi. It repeats itself every 2 pi. Asymptotes, the vertical asymptote is where the function does not exist, which we figured up here at n pi when n is an odd integer. There's no horizontal asymptote because using L'Hopital, if I do that, I end up getting this, which is still just infinity, or it doesn't work. There's no horizontal asymptote. There's no oblique asymptote either. Increasing or decreasing, first derivative test, I use the quotient rule. After the quotient rule, I get this. So here, when does the denominator equal to 0? It happens when x is equal to, I should have put a pi there. When x is equal to n pi, where n is odd. So I should have put a pi where n is odd. So here I get negative pi and pi. Notice this is, but yeah, so when I do this, I realize it's actually always increasing. So it's increasing for all x except at those points, because at those points you have asymptotes. So that's why it is important to know this, because that's where the asymptotes are, but it's always increasing. So one way that Webstein writes is increasing from this point to this point, where k is any integer. Or if you plug it in, it'll end up giving you from every period of pi that we have an asymptote. Okay, now local maximum, there is no local maximum since it's always increasing. Second derivative, you do this, you end up getting this. So you set the numerator equal to 0, and again, same story, sine x is equal to 0. Well, that happens at every 2k pi. So the inflection point is 2k pi comma 0. When the denominator equals to 0, that's where the function doesn't exist. So you end up getting 2k pi plus 1 times pi, which is what we did in finding the increasing and decreasing. The first derivative, we've got something similar to this. So here are where all of the change of concavity is going to happen. So I just picked negative 2 pi, negative pi, 0, pi, 2 pi. So when I plug this into the second derivative, I get positive, negative, positive, negative. So this is going to keep repeating because this is a period that keeps going on. So concave up from negative 2 pi to negative pi. So this is kind of what happens if k is an integer. And concave down from negative pi to 0, which is what happens here when you plug in an integer for k. And it's going to keep repeating. And then when you draw this graph, this is what it looks like. Concave up, down, down. It'll keep repeating in that order as we saw up here. Notice it's always increasing, this graph. However, this asymptotes is going to keep repeating. And notice that it is symmetric about the origin. And it does have a 0, 0 intercept.